Hello everyone. Here we are going to be working on worksheet 11 and it's on chapter 14. The first problem is worksheet 11 and then they wanted you to review problems 4 and 5 from worksheet 10. So I went ahead and copied and pasted those problems from the last PowerPoint. Question 1. Write a scheme of the logic of each glycolysis step. You can use figure 14-3 of your book as an example and explain the purpose of each of those steps. So this is figure 14-3. It's actually one page, but it didn't fit on here, so I divided it here on the left. This is the preparatory phase, and it should be steps 1 through 5. And then on the right is the payoff phase, and it should be steps 6 through 10. However, step 5 was stuck over here. I didn't know how to separate it, so just know that the preparatory phase is 1 through 5. Over here, I went ahead and brought in some relevant definitions from worksheet 10 because they still apply here. A reduction is a gain in electrons. It becomes more negative. An oxidation is when you lose electrons or you become more positive. A reducing agent donates electrons, so it reduces something else. An oxidizing agent accepts electrons, so it oxidizes something else. And so the questions that you have to answer are, what steps are oxidations? So, yeah. Who gets oxidized and who gets reduced? This question is pertaining to this step right here. Whatever step your answer is, you have to say, okay, which of the molecules is getting oxidized and which one is getting reduced. What steps involve production of high energy compounds? So there's several answers here. And how many net ATPs are produced and why? So yeah, just read actually worksheet 10 is going to help you a lot with this. So I'm going to go ahead and read the legend to you. The chemical logic of the glycolytic pathway. In this simplified version of the pathway, each molecule is shown in a linear form, with carbon and hydrogen atoms not depicted, in order to highlight chemical transformations. Remember that glucose and fructose are present mostly in their cyclized forms in solution, although they are transiently present in linear form at the active sites of some of the enzymes in this pathway. The preparatory phase, steps 1 to 5, convert the 6-carbon glucose into 2 3-carbon units, each of them phosphorylated. Oxidation of the 3-carbon units is initiated in the payoff phase. To produce pyruvate, the chemical steps must occur in the order shown. Okay, so I just read that and I just gave you an answer in that paragraph. So if you want to check your answers for this worksheet, you can go ahead and do that at office hours. Okay, for problem number 4, you're going to be using table 13-7 from your book, so I went ahead and put it in here. Standard reduction potentials of some biologically important half reactions. So here you have the reaction, the half reaction, and then you have the standard reduction potential in volts. So as always, we're going to go ahead and start with some vocabulary. Reduction. This is a gain in electrons, so you become more negative. An oxidation is when you lose electrons, so you become more positive. A reducing agent donates electrons, so it reduces something else. An oxidizing agent accepts electrons, so it oxidizes something else. If you are more positive, you are more likely to gain electrons. So now we're talking about the standard reduction potentials. These guys over here. So if these are more positive, they're more likely to gain electrons. And if they are more negative, then they are more likely to gain or to lose electrons. Yeah. So sometimes it'll happen that you will be asked to compare two negative numbers like this one and this one, and from these two, one of them will be more positive and one of them will be more negative, and then you'll just be able to compare that. Okay, so let's go back to our definitions. If you are more positive, you are more likely to gain electrons. When you gain electrons, you oxidize something else, so you are the oxidizing agent. If you are more negative, you are more likely to lose electrons. When you lose electrons, donating them to something else, you are the reducing agent. So here in this problem, let's go ahead and read the question. Standard reduction potentials. The standard reduction potential of any redox pair is defined for the half-cell reaction. Oxidizing agent plus N electrons goes to reducing agent. The standard reduction potential values for the NAD plus NADH and pyruvate lactate conjugate redox pairs are minus 0.32 volts and minus 0.19 volts respectively. Which redox pair has a greater tendency to lose electrons? Explain. So I like to put everything in a table format like you see down here. So we have NAD plus, NADH, and then their standard reduction potential, and then what are they in reference to each other. So NAD plus NADH was minus 0.32 volts, and pyruvate lactate was minus 0.19 volts. So NAD plus is more negative in reference to the pyruvate. So with this information, you should be able to answer the question. Okay, so here's some more information from your book. Why do we use the standard reduction potentials? To predict in which direction electrons will tend to flow. Electrons tend to flow toward the half cell with a more positive standard reduction potential. The energy that is made available by the spontaneous electron flow is proportional to the energy change in the reduction potential. So we use the formula or the equation 13-7 that you see here. Okay. The little n is equal to the number of electrons transferred in the reaction. So the standard reduction potential right here is the standard reduction potential of the electron acceptor minus the standard reduction potential of the electron donor. So whenever you're given a problem, you know that you need to subtract the standard reduction potential of the electron acceptor minus the standard reduction potential of the electron donor. Remember that the more widely separated they are on the table, the more energetic this reaction will be. And F is just 96.5 kilojoules per volt times mole. For question 4b, which pair is the stronger oxidizing agent? So this is referring to part A, and based on all the definitions and information that I've given, you should be able to answer this question. And then for part C, beginning with 1 molar concentrations of each reactant in a product at pH 7 and 25 degrees Celsius? In which direction will the following reaction proceed? You should also be able to answer this question based on the information given. Okay, for question 4D, what is the standard free energy change for the conversion of pyruvate to lactate? So the hint is that this is the equation that you're going to use, and if you go to the worked example 13-3 in your book, they have another example exactly like this problem, so it'll provide step-by-step guidance. And then for 4E, what is the equilibrium constant for this equation? The hint that I'm giving you is that this is the equation that you use. Okay, so number 5 is the first step of chapter 14. So 14.1, that's what section you'll be able to find this information in. So write the 10 reactions of glycolysis, showing the structures of molecules involved, indicating the name of the enzymes, and explaining which of those reactions are A, phosphorylations, B, isomerizations, C, oxidation reductions, D, dehydrations, and 2, carbon-carbon bond cleavages. Based on the free energy changes of each reaction, use table 14-2, so I went ahead and put it over here on the right for you, of your book, shown below. Explain if they are favorable or not, and what is the strategy used by the cells to make non-favorable reactions proceed towards products under physiological conditions. Also explain which reactions are irreversible under physiological conditions. So to answer this question, read 14.1. The book does a great job of explaining everything. In figure 14-2, you have a visual representation of the steps that you're supposed to be drawing. So here's the first 5, and then here is 6 through 10, so that you know what's happening. And then I also recommend that you read the pages that are associated with this figure. Again, they explain step by step what is going on, and I think it's only about 2 or 3 pages. So I went ahead and started you off right here with the first reaction. You see that you start off with glucose. ATP is used. The enzyme is hexokinase, and you end up with glucose 6-phosphate. And you can see that this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and then at carbon 6, you have your phosphate group. So this is a phosphorylation reaction. Okay, so this should be enough information to get you going on this.